Welcome back to the fourth lecture on Waring's problem in the circle method. In this one, we'll wrap up the final details to proving the asymptotic for sums of 5 or more squares. Just to kind of remind you of what that theorem is, of course, this is the case k is equal to 2. We're showing that the number of ways to represent a number as 5 or more squares is satisfying this formula right here. And we finally, at the end of last lecture, got to the singular series. We completed it. And we also completed a singular integral. So the point of this lecture will be to interpret that singular integral as a certain volume. Okay. And to interpret this singular series as actually a product of analogous p-adic volumes for the sphere. Right. And all the previous lectures were devoted to establishing that the error terms are of a smaller order of magnitude than what turns out to be the magnitude of this main term, which goes like n to the d over k minus 1 for k, a degree k equation, which when you're squared, k is just 2, so it's n to the d over 2 minus 1. Right. And again, an important thing that we need to do in order to make this an asymptotic formula is we need to show that the singular series is actually bounded away from 0 and bounded away from infinity, as indicated at the bottom here. So just a moment to take a sip of water and leave on the screen all the notation that's been used. Okay, great. So our specific problem is we're counting the number of integer points on a sphere of radius square root of n. And this counting is an arithmetic volume. What I want to argue throughout today is that counting is actually, the main term is a product of a bunch of different other volumes. Those volumes being a real volume and a bunch of p-adic volumes. Right. Previously, we had a bunch of different steps going into it. We were using a delta method, Poisson summation, Bowles inequality, and so on to peel off a bunch of error terms. These are steps 1 through 6, or 1 through 4. We were peeling off error terms, and then we threw in some extra stuff that was also an acceptable error term in steps 5 and 6 when we completed the singular integral and completed the singular series. And today, we're really on to step 7 and 8 in our proof. We're looking at the singular integral, showing it's positive, grows to the way we want it to, and that the singular series is a product of p-adic singular integrals. I guess I left a slide here in case there are any questions about previous aspects of the proof, any sort of loose ends that people thought I should return to. If you can't think of any at the moment, we can just come back to this again later on, say at the end. Right. We were optimizing the error terms before, and in our optimization, we had 2 parameters at play. We had the big N that we're trying to represent as a sum of squares, and then we had this other parameter R, which is measuring the width of the exponential sum, or the truncation of the exponential sum that came into this delta, came into representing the sum of squares. And we found that in our optimization, we should just set R equal to square root of n. And in doing so, we popped out this following oscillatory integral, c infinity n of r, which was part of the main term. Today, the first step in today, what I want to do is I want to actually interpret this as a volume on a sphere of radius r, which again is equal to square root of n. All right, but that volume, since the sphere is a singular measure, the sphere is a singular body, or it's a codimension 1 subset of Euclidean space, it's going to be a singular measure with respect to Lebesgue measure, right? But this singular measure is a bit different from the usual measure on the sphere, at least when r is not equal to 1. It grows appreciably smaller because we saw before it grows like r to the d minus 2, rather than r to the v minus 1. This should be a big R. Which is noticeably bigger. Okay, so what's our main lemma? Our main lemma is the following. That oscillatory integral is actually the right order of magnitude in terms of n times the volume of the sphere of radius 1. And I'll make precise what I mean by volume on this thing in a bit. Okay. So how do we do this? Well, the first factor, the n to the d over 2 minus 1, is just going to come about by changes of variables. Oh, sorry. I have some notes with this on here. Okay. So how do we do these changes of variables? So I'm going to write this back out as the integral over r e to the minus 2 pi I nt minus nt. That's the integral of phi of x over r, this is rd, e of x squared t dx, then dt. Yeah. Okay, so I'm going to make two changes of variables here. I'm going to send x to square root of n times x, and I'm going to send t to t over n. And when I do that, this becomes, what happens here? Well, I multiply by square root of n. So this is actually equal to an n here, at, of course, the factor of n to the d over 2. It's an n to the 1/2 in each direction. And then I'm dividing by n over on the t's. That takes out a power of n from the Jacobian. And what I'm left with is
Kevin, you forgot to get rid of the r in the x over r.
Oh, thank you. I'll do that in just a moment.
I mean, it's not exactly root n, but
and right, and I forgot to multiply by square root of n here, as Rob pointed out. Right. I've given myself a little bit of flexibility right here. And I've just assumed that big R is bigger than or equal to square root of n. For what we mainly care about, R will equal square root of n, but for the moment, I'm not going to worry about that. And the way I'm going to handle that is I'm actually just going to introduce another parameter that captures this ratio, and little r squared will be defined as r squared over n. So that the above is actually equal to n to the d over 2 minus 1 times the integral over r, and integral over rd, phi of x over little r. And also little r is going to always be greater than or equal to 1. And then I have e of t times x squared minus 1. That's with respect to dx and then to dt. Okay. Hopefully that's clear. That's just changes of variables. Those changes of variables are fine because we've already shown that this integral is absolutely convergent in terms of the outer integral. This one, right, is absolutely convergent. And the inner one is also absolutely convergent for each fixed t. But altogether, it's not absolutely convergent in terms of x and t simultaneously. But that's, we just need to be able to integrate each one individually. So that's cool. Great. So what we see is that we actually care about calculating this double integral. And again, this double integral is not absolutely convergent in terms of x and t simultaneously. If I were to apply the triangle inequality and take absolute values, right, this term cancels. The absolute value of this thing is equal to itself. And I haven't said anything about t. This is some about where I calculate the volume in terms of x. That's some fixed number, and it's fixed for all t, so the whole integral would be infinite. But that's not what's happening here. We actually are caring about the limit as the limit in t. Okay. And what do I mean by that? I mean, I'm actually, this is equivalent to the limit as, say, t tends to infinity of the integral of, and I'll put chi of t over t r, the integral of phi of x over r e t x squared minus 1 dx dt, again in this order. Integrate with respect to x and then t. Now where chi is a Schwartz function, it's Schwartz, say its integral is 1, the integral chi equals 1. And if you want, it's 1 at the origin. Yeah, say 1 at the origin. And it's always non-negative as well. Okay. Now what happens is as t goes to infinity, so I have some little bump function chi, maybe looks like this. That's supposed to be the origin. Got a little bump function here, and as t goes to infinity, this is getting smoothed out. So I'm incorporating more and more mass of r, but always at most bounded by 1 as well. But I basically, in the limit as t goes to infinity, I'm approximating this function that's 1 everywhere, right? So that this limit is just a smoothed out truncation of the above integral, right? Which I said is absolutely convergent. So this, by just basic calculus, this limit is equal to that integral, right? Let me grab a little more t. Okay. Are there any questions about this truncation at least? So the reason I'm doing this is now each truncation is absolutely convergent, right? If in both x and t, because chi is Schwartz. When I integrate with respect to x first, that's some absolute bound, and then since chi is Schwartz, the integral of that absolute bound against chi is just some other finite number. And that finite number grows with t, which is super important, right? Because the whole, as t goes infinity, there's no absolute convergence, but at each stage there is, and that's sufficient for us. So we can actually rewrite this as, this whole thing is, right here is equal to C infinity of 1r. And I'll write each of these, having fixed chi, write each one of these as just C infinity of 1r and t. Okay, the truncations. Now that I have absolute convergence in terms of for each fixed t, you can apply Fourier inversion, right? And when we do that, we find that I just apply the Fourier transform. So I'm going to apply Fourier inversions, right, with respect to t now. Well, how can I do that? Well, I have an absolute convergence thing in terms of x and t. So apply Fubini's theorem, switch the order of x and t in integration, and apply Fourier inversion in the t variable. When I do that, you get the following identity. So C infinity of 1r and t actually looks like this. Why is that? That's because the Fourier transform of chi of, so the Fourier transform, that's how Fourier transforms work with dilations, right? If I look at this chi hat is the real Fourier transform. So chi hat of C is equal to the integral over RD of chi of x e of x dot c dx, right? And so if I this is actually a one-dimensional, sorry, it's one-dimensional because chi is one-dimensional. And right, so if I take chi of t and I dilate by t, right? So I look at x over t here. I'll call that chi of t. Then when I do the change of variables, I multiply x by t. That puts out a t here and a t here. And so I get chi hat of t of c is equal to t chi hat t of c, where chi of sub t was defined as at a point x is just is chi of x over t, right? And now this integrating over it also picks out the value x squared minus 1. Great. And if we had picked chi so that is Fourier transform. So I picked chi to be non-negative because I always wanted it to, as t goes to infinity, go from this little bump function to the function that's constant everywhere and equal to 1. Now, when if I picked the Fourier transform always to be non-negative as well, then I can see immediately that this last expression is non-negative. And actually, you can do that. You can take a Schwartz function and you can have one that is Fourier transform is also non-negative by just taking, I think it's just look at, if I start with one chi and it had negative values or even complex values, I just replace it by chi involved with its conjugate. And then that is now one that has a non-negative Fourier transform because the Fourier transform turns convolution into multiplication and the conjugate goes through so that I have now a square of, I have chi in absolute value squared when I take the Fourier transform. And that's a square is not negative, right?
Yeah, I mean, but so far we could have just used the Gaussian. There isn't any reason
and
not
that is
to.
a good example of a function that has this property. But I tend to eschew special functions when I can get away with it. But yeah, I think Rob makes a great point. A very good example to do this is take chi to be a Gaussian.
And that's e to the minus pi x squared.
And yeah, the normalized one. so that it interacts, because I've chosen my characters to be e to the 2 pi I, then this pi is also the right one to do. And yeah, this is a Schwartz function. It has all the nice properties that I wanted. It's let's say usual function of choice when you want to prove Fourier inversion, which is what I'm using here. And yeah, it's great for this one, but it's not strictly necessary. You can pick a lot of other Schwartz functions as well. Great. Yeah, okay, now that we have that this, so chi bar, sorry, the Fourier transform of chi is also non-negative, we see that this thing is non-negative. All right. You can also see that from just thinking about it for a moment, you can also see that if you take, say, r equal to 1, then that's a 1 here, so that is just phi of x. When I look at this integral, so this is also going to be actually positive, because chi will be non-negative, but it also has to be positive in some neighborhood around 0, because I chose a Fourier transform of chi at 0 to be 1 when I made this stipulation right here. And since it's Schwartz, it's positive around 0 for a small neighborhood, right? So that means that this is actually going to be positive for r equals 1, because this contains the phi is 1 on the cube from -1 to 1. Therefore, it contains the sphere of radius 1 centered at the origin, right? It's this versus, see if I can draw a sphere inside. Okay, artistic interpretation of a circle inside. And so you actually get that this is positive. Now, I don't actually care, again, I don't really care about special functions. You can compute this value precisely. And I indicate in the notes how to do that. You can consult Davenport or Vaughn to actually get this as a representation in terms of gamma functions or special values of gamma functions. However, that's not the point I want to make. The point I want to make is really, this is actually a volume on the sphere of radius, well, radius 1. Okay. So how do we see that? Well, this thing, that this chi and the Fourier transform of it, which you can think of as a Gaussian, so that its Fourier transform is just itself, that the Fourier transform of e to the minus pi x squared is, again, e to the minus pi x squared. Then what happens is, when I look at these functions, s times the Fourier transform of chi multiplied by s in the argument, this tends to the delta function as s tends to infinity. So these form an approximation to the identity. What's called an approximation to the identity. This is the digression, especially for number theorists. So this forming a one-dimensional approximation to the identity. Where's that name come from? That's any family of functions which are at least distributionally converging to the delta function. And they're called an approximation of the identity is because when you convolve with the delta function at 0, that is just the identity operator, at least as a distribution. This approximation of the identity, though, it's not quite the delta function. It's just the delta function in the limit. So that convolution of that family converges to the identity in the limit. And the way this is typically done is you start with some Schwartz function and you consider all the L1 normalized scalings of that function. They're L1 normalized because you want to take, I'm going to convolve with something, and Young's inequality tells me that I should normalize things in L1. Now, once you have that, it's it's a calculus exercise to show that if you start with some function and that's, say, continuous, and you consider an approximation of the identity, and you look at those convolutions, then it turns out that those return, they are exactly what I'm saying. They are an identity in the limit, right? If I
So
take,
Kevin, I don't want to be a pill here, but you technically also need f to be bounded.
not at each point. So maybe I have the order of quantifiers wrong in the conclusion. If I just look at a point, for each point, and I look at the limit as it goes.
No, you still need f to be bounded because there's no guarantee that that integral will even converge. Well, okay, you need f to be slowly growing, I guess, if you're using a Schwartz function.
Oh, right. Okay. Yes. So, yeah. Okay. Say f is in. Yeah. Okay. So.
Yeah. Sorry, I'm being a pill. I know.
Let's say the integral of f is finite. Yeah. No, that's a great point. When I'm thinking about continuous functions, I'm thinking about well, I'm actually thinking about step functions, which are technically not continuous. But yeah, I'm thinking about something that has an L1 norm. Yeah, you're absolutely right. Yeah. So assume that it has a finite integral. And that's because, as Rob's trying to point out, if I look at the integral of f involved with g of epsilon, then was it Young's inequality tells us that this is less than or equal to, well, I'm sorry, if I look at the L1 norm of this, less than or equal to the L1 norm of f times g of epsilon. And I've rigged things up so that this latter one is always 1. Right? And so one condition I haven't said, but it's on the slide, is that I want the integral of g of 1 to just be 1. And that means that g of epsilon, for all epsilon, is the integral of that is also 1. Yeah. Thank you, Rob. Yeah, but taking these for granted for the moment, the approximations identity, basically in the limit, what I've said is that these factors Cn of r, C infinity n of r, are equal to this integral. And this integral is a singular, is using a singular measure on the sphere. Because the delta function is a singular function, right, in R. The delta function is 1 at 0 and 0 otherwise. But to make that that's not even quite correct. It's really just saying when I look at the inner product of delta with the function, it's that function evaluated at 0. So it's you have to think about delta as a linear functional. And the way to make this all rigorous is to use these approximations of the identity and use this proposition, right? And which, when you're using the proposition and you're looking at, say, f is also Schwartz, you automatically don't have to worry about that boundedness issue that Rob pointed out. Oh, okay. This the way I've said it, actually, I'm really needing that r is greater than or equal to 1. Right? That's the relation between n and r here, and that was so that when I plug in this singular measure here, I'm actually looking at functions that contain the sphere of radius 1. If my function didn't contain it at all or intersect with it, the support of that function didn't intersect with that radius, that sphere, then I'm not going to pick up any mass on the sphere in any way. So I need it to contain that. And once I do that, this is what I mean by the volume of the sphere. Okay. It's what this limit is equal to. Once again, that is positive, sort of, which you can see by pure thought. And the precise value of it isn't super important for us. It's nice to know, and it can't be computed in terms of gamma functions. Are there any questions on this? I'm going to assume everyone's happy now because Rob has, I think, filled in any gaps or omissions I had there.
Yeah, again, sorry about being a pill.
No, you're not a pill at all. That's great. It's very good points. Thank you. But Just to give anyone else a chance to ask, take a sip of tea. Great. So let's move on to the singular series, which we completed last time. And just to recall what that is, it was this sum of Gauss sums. And each of the Gauss sums is at some rational point, A over Q, which I just parameterize as the pair AQ. And they're also, I had a linear factor that came into them in their definition when we did the Poisson summation. But we showed that the zeroth frequency was always the biggest one. And so we always get to set that linear part to 0. But we'll keep it in here in any case. It's what it is when you write it out. It's just this bigger, longer written exponential sum, right? Remember that even though b is in z mod q to the d, this expression just means sums of squares. There is no absolute value on z mod q. Not well defined, at least, and that's over all the coordinates. Okay. We saw that this series is absolutely convergent for d greater than or equal to 5. Meaning when I take this and I say it's less than or equal to the absolute value of this, that term is just a 1 now. I move this over here. And I look at the absolute values of G, of the Gauss sums. We had the bound coming from Weil's inequality. We had that G, A, Q, and for a general M, we had that this was true. Oh. Q to the minus D over 2 plus epsilon for all positive epsilon. I said, but I didn't prove, I'm leaving it as an exercise in those, that we have a better bound. We actually have that this is less than or equal to 2 to the D, Q to the minus D over 2. For all M, all Q, all A. That's because you only have to prove this in one dimension. Remember, these Gauss sums are tensor products of exponential sums. So that if I have G of A, Q, M for some vector M, is actually equal to the product I equals 1 to D of a one-dimensional Gauss sum of D one-dimensional Gauss sums, which for us, when we plug in M to be 0, just means it's a product of GAQ0, the one-dimensional version. So just that to the dth power. Great. The point I make about the reason I recall that this is absolutely convergent for 5 or more dimensions is that we can rearrange the series as we like now. It's absolutely convergent in terms of A and Q as a double sum, which was different from the singular integral a moment ago. But we can rearrange a series as we like. So that's cool. Why is that useful? It's going to be because of the multiplicativity in these Kloosterman sums. So what are the Kloosterman sums? For our purposes, this is not the typical definition. It's just picking out one of the terms depending on the modulus Q. So I take for each modulus Q, and my n is fixed, right, from the beginning, I look at this exponential sum. It's normalized by Q to the minus T. Normalization came from the Gauss sums before. Right, this is an average over all B on Z mod Q, but then an average over all units A modulo Q. The main proposition, the main insight here is going to be that the Klusterman sums are multiplicative in Q, in the modulus. That is, if I take Q1 and Q2 coprime, then the Klusterman sum of Q1, Q2 is equal to the Klusterman sum of Q1 times the Klusterman sum of Q2. Now, I've been a bit sloppy here, but just to cover my bases, when Q is equal to 1, I'm just going to find the Klusterman sum to be 1. There's only going to be one term to consider, and it's just going to be, so that's 1. Okay, and therefore, this makes sense when I take, say, Q1 to be 1 and Q2 to be Q, this proposition. typically Klusterman sums are defined differently because there's a way to massage those sums, the ones I've written down that have the quadratic characters in them, in terms of something involving a variable and its inverse. And that's easier to analyze from an algebraic geometric point of view. For us, though, we don't need to do those. We don't need to massage things like that because we're not caring about the additional cancellation that lies in a Klusterman sum that you don't see from the triangle inequality we've applied that destroys the cancellation in this character, coming from this character. That's not something we need to concern ourselves with. But it is important if you want to talk about dimension 4. Right, so once we rearrange the series, so how are we going to rearrange the series using this? Why is this multiplicativity important? Well, we can take each, so things are multiplicative, meaning I can decompose each modulus q in terms of its unique factorization, in terms of powers of primes. I can collect those individual powers of primes into their own sums and take a product over all possible primes. I just use unique factorization for integers into primes. And that allows us to write the singular series as a product of a bunch of other series. But each of those series only depends on one fixed prime, and the series goes through all the powers of that prime. Now the second main insight here is that each one of those subseries, coming from the product, actually has a physical characterization that is the measure of a p-adic sphere, is the volume of a p-adic sphere. So to get to that, we'll introduce a notation. So I had before C infinity of n. Now I have a Cp of n for each prime p. And it's this, and initially it's going to be this exponential sum. So the singular series is a product over all of those factors. Now the absolute value, the absolute convergence of our singular series tells us that when we do this product, those series have to tend to, that each of those factors has to tend to 1 as p tends to infinity. Otherwise, you can't make sense of the product, right? That's much like series, a series has to converge to 0. The absolute value of its individual terms have to converge to 0. The same thing with a product, it has to converge to 1. Right? But we actually know more. This Gauss bound that I mentioned before, the fact that the Gauss sums are bounded by 2 to the d times p to a certain power, tells us that we actually have, we know it's quite close to 1 when p is large. And we know how close it is in terms of the dimension d and the prime p. And it's just done this by summing up a geometric series. Okay. And you see off the bat, just when p is sufficiently large, say p is bigger than 100 and d is at least 5, that these terms are pretty close to 1. But this error term, this error term right here, is much bigger than 1, unfortunately, when p is quite small. For instance, if p equals 2, then that factor of 2 to the d is blowing up the error term too much. Nevertheless, we can actually say that we're bounded away from 0, that our singular series is. So what I want to say right here now is that the singular series, which I am not good at drawing, that, by the way, is a math frac S, which looks to me a lot like a G. Took a while to figure out how to type that in LaTeX years ago when I first came across it. Yeah, but it's a math frac S. So this thing is at most, well, it's like product of 1 plus 2 to the d over 1 minus p to the 1 minus d over 2. Oops, times p to the 1 minus d over 2 over all the primes. That is really just at most a product over all primes, 1 plus p to the 1 minus d over 2, which one might realize is just zeta, the zeta function, the Riemann zeta function at 1 minus d. Oh, sorry, d over 2 minus 1. Inverse. No, wait. Yes. Great, so it's pretty small. Or it's, I mean, it's not pretty small. It's bounded away from infinity. It's bounded by some absolute number, which is good for us because if we want an asymptotic formula, then we need to make sure that this singular series isn't blowing up to infinity, right? Similarly, we also need to show that it's bounded away from 0. But we haven't done that yet. This error term is a bit too small. Sorry, a bit too large. Remember, if I took p equals to 2, I don't know that I'm close to 1. That error term is big enough to where it could say that C2 of n is 0. And then if I have 0 in my product, everything's 0. I'm just killed from there. But what does that mean? That means that we're going to have to do something else in order to get around that. And we only have to worry about that because of this Gauss bound. We only have to worry about that for small primes. We don't have to worry about that for big primes. It's only like 2 and a few others. Okay. And we'll show that CP is greater than 0 for every prime. And then once we know that it's greater than 0 for every prime, it's in particular greater than 0 for the small ones. And all the big ones are close to 1, so that the whole singular series is bounded away from 0. And that's done uniformly in terms of n. We'll come back to that after we handle the multiplicativity. Were there any questions so far? Okay. Multiplicativity of the Klusterman sums actually relies on multiplicativity of the Gauss sums. Remember that the Gauss sums for us were just G of A, Q, M is defined as the sum over B and Z, Q to the D, E of A, B squared is B dot M. Over Q. We had M equal to 0 though, for simplicity. Let's just do that. So these terms disappear. And we really just have my claim is that these are also multiplicative. In what sense? Well, I have to worry about this A that comes in defining the Gauss sums. And that A depends, that A is related to Q1 and Q2 in the following way. So if I pick my moduli Q1 and Q2, I want to show that G of A Q1 Q2 is just like G of A times G of A Q1 times G of A Q2. But instead I have to think about what happens to A when I reduce it modulo Q1 and modulo Q2 separately. It has a unique representative for each one of those. Right. To prove this, this is just an exercise in the Chinese remainder theorem, basically using what I just said. If I fix my two coprime moduli, Q1 and Q2, I have an isomorphism between Z mod Q1 times Q2 with Z of mod Q1 times Z mod Q2. And the way you do this is there's a way, there are a bunch of ways to do this, but the one that'll work best for us is I find two integers, M1 and M2, satisfying this linear Diophantine equation. Why is this possible? This is possible because Q1 and Q2 are coprime. That means that their ideal in Z generates the whole ring Z, right? So it's equal to the ideal generated by 1, which is a unit, and ideals are just linear combinations, right, of integers in this case. And that means I can find two integers, m1 and m2, whose linear combination with Q1 and Q2 is 1. Now that I've done that, I take B and I multiply it by 1, written this way, and that gives me two pieces of B now when I distribute the sum. And that allows me to define a B1 and a B2 in Z mod Q1 and Z mod Q2 respectively as such. I take out the Q part of it, the Q1 and Q2 part of it respectively. And when you do this, I can rewrite each B as B1 times Q2 plus B2 times Q1. And that gives me the isomorphism between these two rings. Are there any questions about that isomorphism at the moment? Great. Now let's just go through and show that these two things are coprime now. Remember, G of A Q1 Q2 at 0 is just Q. Oh, first, to make my life easier, as I said before, this is actually just D times the one-dimensional version, right? So I just have G of A Q1 Q2 of a scalar 0, of a one-dimensional 0, to the dth power. That means it suffices to just prove this for the one-dimensional version. And that's what I'll do. Great. Now let's do that. Remember that G of A Q1 Q2 of 0 is Q1 Q2 inverse, it's normalized, times the sum of B in Z mod Q1 Q2 EA B squared over Q1 Q2. I'll plug in my formula for B right here. Okay, I haven't done anything yet. Well, this B1, B2 is in Z mod Q1 cross Z mod Q2. Right, I've made use of that isomorphism now. We open up the square over here. When we do so, we'll see that the cross terms are going to cancel out, or well, they're going to be divisible by Q1, Q2. So that means that they won't, it's just going to be multiplying by 1. Okay. Oh, what did I do? Increase. Let's do that now. This is equal to Q1, Q2 inverse, sum over B1, B2. And it's now E of A B1 Q2 squared plus A B2 Q1 squared all over Q1 Q2. Oops. Well, we can rewrite that as not do that. That is simply A B1 squared Q1 over Q2. Nope. Q2 over Q1 plus A B2 squared Q1 over Q2. And now we pull apart the two sums, the double sum. As that. And of course, I'll put my Q2 inverse over here with this sum and my Q1 on that one. Now, Q2 is coprime to Q1 and conversely, because this is a symmetric relation. And A is also coprime to both of them, to Q1 and Q2, because it's coprime to their product. That means that I can divide through the first sum by AQ2 at just the expense of permuting the B1s. And similarly, in the second sum, which is acting independently now, I can divide through by AQ1. This is just permuting the B2s. So this is actually just equal to I'm going to divide through by Q2, sorry, not AQ2. And then by Q1. Oh, Q2 inverse. That looks terrible. Let's rewrite that. And now we just plug in the definition of the Gauss sums at these two values. This is just G1 of, this is just GA Q1, at 0. That's just G of A Q2 at 0. And you just think about now A as A mod Q1 is my new A1 and A mod Q2 is my new A2. And that's the multiplicativity that we wanted. Were there any questions about why that was true? Well, I'm going to just now take the easy way out and say that the proof of multiplicativity of Klusterman sums is an exercise. It's basically the same argument, but you throw in the isomorphism between the unit groups. Using it's the same isomorphism as before in terms of writing each number as a linear combination of Q1 and Q2. And now you just use that combined with the multiplicativity of Gauss sums and the complete multiplicativity of characters E of these sorry, where is it? Of E minus A n over Q. It's completely multiplicative. It's a good exercise to make sure you're happy with the multiplicativity of Gauss sums. All right, I will pause there for the end of lecture 4. Were there any questions before I do? For anything up until now? Brilliant. Let's pause and come back.